In fact, it is going to increase with the frequency. So we have seen, see here, I and G is proportional to omega square. So it is going to increase as at high frequency operation, my gate noise is going to be very, very large. So I cannot say the spectral density is going to be constant. So to analyze that in optical term, initially we call the thermal noise to be white, but now we change it to blue noise because blue noise is going to be considered to be the extreme end of your optical spectrum of the visible light. Okay, with GR, indigo, violet, indigo, blue. So blue comes third, right? Third in terms of wavelength, but in terms of frequency, it comes last. So we can say that from white noise, we slowly move to the analogy which is called as blue noise because this gate noise is going to be increasing with frequency. So for those who prefer not to analyze systems with blue noise sources, so definitely this model will clearly, wherever if you want to include analyze the effect of gate noise in FET, we'll be including this equivalent circuit in the circuit, and we'll analyze what is the effect of this noise current which is happening in the gate. Okay, so this simplified circuit is very much mathematically also it is correct, logically also it is correct. So this circuit can be inserted as and when in your electronic circuits to analyze the effect of gate noise in MOSFETs. So either you can have a current source parallel to GG, or you can convert this current source into voltage or series with GG, and you can go with the computation for the noise in the MOSFET. Okay, so this generally it is given current source parallel to GG, but you can see here now the it is converted into voltage source in series with RG. So it is also easy to convert the either you use the Thevenin's equivalent circuit or you use the Norton's equivalent circuit. You can definitely analyze whether you want to analyze the circuit in terms of RMS value of voltage or RMS value of current. So you can convert the series RC into parallel RC, and you can analyze all these formulas are given, but we don't want all these in depth. We just want to know that two sources of noise is there in MOSFET. One is a drain current noise and one is gate noise. And we have seen what is the model for gate noise. So I think that should be sufficient for you. And finally, the equivalent noise voltage can be given by this equation 4 kT delta RG into delta F. So this is going to be the equivalent RMS noise voltage which is available in the gate noise of your MOSFET. And here we can see the dependence of F is not there. Here you can see the dependence of F. So delta is a constant, Rg is going to be your resistance. So you can see this expression for noise is going to possess a constant spectral density. Constant spectral density means it is going to be independent of frequency because there's no F term present here. But previously in the expression for current, you can see we had an omega term. You know omega equal to 2 pi F. So definitely the whenever F comes in your expression, it means that there is a very strong dependence on the frequency in the noise power of your circuit. But here in the modified equation, we don't have the term involving frequency is coming. So I can say it is going to have a constant spectral density.